In this video, we take a look at the alternating series test, and we're going to take a look at this Taylor polynomial for the natural log of x. In the previous video, we developed this. We also looked at the open interval of convergence, which is found by applying the ratio test to this. Well, we're beyond that now. What we want to do is possibly expand this interval of convergence to include one or both of these endpoints. And the first thing we're going to try to do is plug 0 into this Taylor polynomial. So you do that, and it looks like this. P of 0 equals, okay, here's 0 minus 1, 0 minus 1, 0 minus, these binomials all will now take on the value of -1. So that looks like -1 minus 1/2. Here we have -1 squared. Then we go to plus 1/3, -1 cubed, minus 1/4, -1 to the 4th, etc. Now, it turns out that every single one of these terms will have a negative value. This one we don't need to explain, but here -1 squared is 1 times -1/2 is negative. Here 1/3 is positive, but -1 cubed is negative. Even on this one, the 4th power of -1 is positive, but multiplied by -1/4, it's negative. So all these terms are negative. And I don't need these powers of 1 here anymore once I make that observation. And because all the terms are negative, you can factor that negative out, and you're left with something you're supposed to recognize. This series is called the harmonic series. And what does it do? It diverges. It adds up to an infinite value. And if you ran the divergence test on it, the nth term as n goes to infinity is 0. And you need to remember the divergence test is not conclusive when you run the test and it comes out to 0. But anyway, for a variety of reasons, this thing is infinite. So are we going to be putting 0 into this polynomial ever again? No, we're not. This open interval of convergence is strict on its left side. But what about on its right side? What would happen instead of plugging in 0? What if we plugged in 2? So let's take a look at that for a second here. All these binomials with 2 here for x will be 2 minus 1, 2 minus 1, 2 minus 1, and of course those all equal to 1. So I'll write down what that looks like. It's 1 minus 1/2, 1 squared plus 1/3, 1 cubed minus 1/4, 1 to the 4th, etc. And these powers of 1 are not consequential, are they? Because, well, they're never going to make -1. They're just going to multiply these fractions by 1. So what you end up getting is something like this. Taking away all those powers of 1 and just looking at this series, we get this. Now, unlike the previous one, it's not all negative. It does what we call strictly alternating, positive, negative, etc. Some other highlights are that if you take a look at the nth term, and its absolute value anyway, is 1 over n. And the limit as n goes to infinity of that, of course, is 0. So I have no evidence that this thing is going to diverge. The divergence test comes out to 0 and does not allow us to say that this series diverges. But if you take a look at any of these two terms, this is really important. 1/2 is closer to 0 than 1. 1/3 may be bigger than -1/2. But in absolute value, 1/3 is closer to 0 than 1/2. And 1/4, 0.25, is closer to 0 than 1/3, 0.333. 1/5 is closer to 0 than 1/4. This is 0.2, this is 0.25. That pattern all the way through can be generalized. If you say the nth term is 1 over n, what's the absolute value of the n plus first term? And no, I don't care if they're negative or positive at this point. It's 1 over n plus 1. And so for positive values of n plus 1 is bigger than n, which makes this quotient smaller than that, or closer to 0. And that's true all the way through, and that's the generalized argument. So this series is going to converge by the alternating series test, which we will introduce formally in just a minute. But before we do that, there are different ways to argue that this converges. I mean, I've seen where people will, they'll group these two terms, they'll group these, they'll associate these, and then all the values of those groupings are positive. So they'll say, well, this is a grouped like this is a series of all positive terms. And then they'll group it a different way, where they group these two, and they group these, and they group these, and it'll end up looking like a 1 minus, 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 and they'll say, aha, it's bounded. So it's all positive looking at it one way, it's bounded looking at it a different way, this thing converges. Those are really good arguments. I'm not here to, throw shade on those arguments. But I like this argument better. This argument says, because the three conditions of the alternating series test are met, the way this thing converges is 1 is the very highest number you'll ever see in terms of partial sums. The second partial sum is where you subtract a half from 1, bringing the value down to a half. That's the lowest number you'll ever see. How do I know all those two things are true? Well, what's the third thing that happens for the third partial sum? You add a third. That brings the total back up to 5, 6, but see, that's lower than where you started. In other words, adding a third is a smaller gain than subtracting a half. Now what happens next? We subtract a fourth. Okay, so third partial sum was 5, 6. I'm going to subtract a fourth. Now we're down to 7/12. But 7/12 is not as low as a half was. Because having just added a third to get up to 5, 6, we now subtract a fourth, which doesn't take you down as low as you were back here. And if that is hard to follow, let's just take a look at a graph that shows these partial sums. First partial sum was 1, second was a half, the third was 5, 6, the fourth partial sum was 7/12, the fifth partial sum, is 47 over 60. And so forth. So the look is start high, drop a lot, climb back up but not as high as you were, drop here but not as low as you were, and this is just going to funnel into some number. What number is that? It's the natural log of 2. Okay, so that's an introductory motivating example. Let's take a look formally at what the alternating series test says. It says you've got this series of terms, T1, T2, T3, so forth. If these three conditions are met, then you can say with certainty that this series converges. And not only does it converges to a number somewhere between 0 and the first term, which could be a positive or it could be a negative. These three conditions are, and I'm going to go fast because we've already talked about these, the terms must strictly alternate. So if you're looking at a term that's negative, you better have positive terms left and right of it. It's got to go plus, minus, plus, minus. Second, this is just the divergence test, but if you took the limit as k goes to infinity of the kth term and got something other than 0, well then this would have to diverge. So we need this to be equal to 0. We need the terms to strictly alternate. And last but not least, the terms need to have a strictly decreasing absolute value. And we've talked about that. So this has got an absolute value smaller than that. This has absolute value smaller than that. And that pattern needs to hold. And then again, the conclusion is once these three conditions are met, you have a convergent alternating series. It converges to a number somewhere between 0 and the first term. And then there's this business down here about the, this is called error bounding. And we're going to get into that soon, but let's keep rolling. Okay, new example. I think this is a mistake. This is supposed to be 1 over 1, but show that this series converges, or maybe that it doesn't. Maybe it diverges. And do this in terms of the three conditions of the alternating series test. Well, I already know the answer, and I'm going to get straight to the one that shows that this does not converge. What is that? Well, take a look at the nth term. And it just depends on how you start counting this, but I'm going to start counting with 0. So here's my term indices: 0, first, second, third, fourth term, etc. The nth term in absolute value would be 1 over 2n plus 1, right? for example, the fourth term, 2 times 4 plus 1, 8 plus 1 is 9. There's your 9. What's the limit as n goes to infinity of that nth term? Well, or absolute value, I guess, if you want to put it on there. That's the limit as n goes to infinity of 1 over 2n plus 1. That's clearly, oh, I forgot the n up here. All right. This is clearly not 0. This has got a form of infinity over infinity. What does that mean? It means you should apply L'Hopital's rule. So the derivative here is 1. The derivative down here is 2. The limit as n goes to infinity of a constant like a half is just a half. And that's not equal to 0. So by that divergence test, this thing diverges. And remember, the divergence test is one of the 3 conditions that has to be met. It has to come out to 0. All right. New example. S is the Taylor polynomial expanded at 1, natural log. The Taylor polynomial, this is just example 1, except we're going to do something different with it. We're going to put 2 into that Taylor polynomial, and we're going to show that the absolute value of error in approximating natural log of 2 with the 9th partial sum is less than 0.1. Okay. Well, this was the result we got when we plugged 2 into that Taylor polynomial for natural log. Here it is. And if you want this to equal to natural log of 2, you have to take all the terms. Okay, what happens if you only take 9 of the terms and you go to here? Well, then you can't have the natural log. You have to have something either bigger than the natural log or smaller. But here are the values of these two things. As you can see, they're not the same. It looks like our 9th partial sum is bigger than the natural log of 2. So if your goal was to calculate natural log of 2, you have error. And error is defined to be the difference between these two things. So let's take a look at that. The error in this is the difference between these. So for example, if I take natural log 2 and subtract the 9th partial sum, I'm subtracting these two things here, and I'm going to get, this is the amount of error there is. Okay, well, I'm not quite interested in exactly what the error is. I would like to know, is there a way to put a bound, an upper bound on the error and say my answer can't be any farther off than this upper bound for the error? To see what that is, all you have to do is understand what's going on here. I'm subtracting, this is S9 here, right? I'm subtracting that from both sides of this equation. And that's leaving me with everything over here, the tail of S9. Okay, so subtract these 9 terms from both sides of this equation, and you get natural log of 2 minus S9 over here. And these are gone. And now you have just what's called the tail of the 9th partial sum. Well, this tail is itself an alternating series, and it converges to a number between 0 and its first term, negative 1/10. Now, I have to tell you, when we talk about error, we usually put absolute value on it. We don't care if it's too high or too low. We just want to know how far off. And for that reason, I would put an absolute value around this tail, which again is negative 1/10 plus 1/11 minus 1/12, etc. But that tail has a value closer to 0 than its first term. So I'd write less than the absolute value of the first term, which is 1/10 or 0.1. And that's how I know my error is no worse than that. It has everything to do with the first term of the tail. And indeed, if you look at the absolute value, my error is smaller than 0.1. Okay, so that's called error bounding. In order to understand that, I went ahead and made a spreadsheet where I took a look at the partial sums of the tail of the 9th partial sum, if that makes sense. Okay? So here's the tail of the ninth partial sum. Here are its terms. They're in the first column here, or second column. But in this column, I'm adding up the first term, and then here I'm adding up the first two terms. Here I'm adding up the first three terms. And as you can see, those partial sums start at negative 0.1, and they gradually work themselves closer and closer to 0. In fact, over here, this is the 40th, actually the 49th, no, excuse me. This is about the 40th partial sum of the tail of S9. And it's a lot closer to 0 than the first term of the tail. So this is closer to what the actual error is between the ninth partial sum and our natural log. And here's a little diagram or an image that shows you the partial sums of the tail. Remember how I said our error between natural log and the partial sum, the ninth partial sum, has to be closer to 0 than the first term of the tail. Well, that first term was negative 0.1. And the tail ends up converging to some number that looks like it's about roughly halfway between 0 and negative 0.1. So this puts the first term of the tail of the ninth partial sum, puts an error bound on just how bad the ninth partial sum was. The worst case that the ninth partial sum could be for calculating natural log of 2. Okay, quickly here, we have an alternating series in example 4. We're supposed to discuss whether this thing converges or diverges. Actually, it says we know it's going to converge to a negative number L. So that must mean that the three conditions of the alternating series test are satisfied. Is that right? Well, negative, positive, negative, positive. We have strictly alternating series. That's good. Second, if you look at the absolute value of the nth term, it's something like 1 over square root n. Okay, I don't need to tell you that that goes to 0 as n goes to infinity. So that's another condition that's important. And then take a look at the term just to the right of this. Its absolute value looks like this. It's 1 over the square root of n plus 1. Well, n plus 1 is larger than n. Square root is an increasing function, so the square root of n plus 1 is larger than the square root of n. So if the divisor here is larger than the divisor there, then the value of this fraction is smaller than that. What am I saying? I'm saying take two consecutive terms. The one to the right will be closer to 0 than the one to the left. It's true here. 1 over root 4 is smaller than 1 over root 3. Closer to 0. It's true here. It's true everywhere. And so this satisfies the three conditions of the alternating series test. So it's got to converge, and it's got to converge to a number between 0 and its first term. Now, if we believe all that, and we should, this number L can be calculated by adding up an infinite number of these terms. Well, we don't have time to add up an infinite number of terms, so we want to take some partial sum, and we want to know that it's it's different from the real answer by at most 0.01. The question is, how many terms would you need? And the answer is a lot. So let's go like this. S sub some subscript here. That'll tell us what the partial sum is. We'll leave that off for now. But it's going to look like this. Negative 1 plus 1 over root 2. You can see it up here. Minus 1 over root 3. And dot, dot, dot. And way down here, you're going to have this term that looks like plus 1 over the square root of 9,998, followed by something that looks like this. And obviously you have to go way down the line here and have a lot of terms. How many terms? I think you need 9,999. Why is that? Well, if you just stop right here, you're computing the 9,999th partial sum, and it has a tail that looks like this. it will go plus 1 over the square root of 10,000. Then it'll go minus 1 over the square root of 10,001. And then back to plus, and so forth. Well, if you don't count all the terms in the tail, then you're never really going to get to this limit L. So there's error in saying that this is the eventual limit. But how bad is that error? It's equal to the value of the tail. And the tail adds up to something closer to 0 than its first term. So we write something like this. The error has an absolute value between the 9,999th partial sum and the real answer L. They're not the same. But the error, which is this difference, has got to be smaller than the first term of the tail of the 9,999th partial sum. Why again? Because the tail adds up to something closer to 0 than its first term. Well, what is the square root of 10,000? And the answer is 1/100th. And that's equal to 0.01. So that answers the question. How many terms would you have to have? That's a lot of terms. All right, we have another example here. Tangent inverse. The Maclaurin polynomial for tangent inverse is this. And it's got an open interval of convergence of this, which you can establish with the ratio test. But after establishing that any number strictly between -1 and 1 is okay to plug into this, and this will converge, we often want to ask, well, what about the actual endpoints? Can we bring those along too? And I can't remember. I think we can do both of these. But in this video, we're only going to look at that one. So we're going to show that plugging 1 into this is a convergent alternating series. And then we're going to discuss something about using this to compute pi. Okay, plugging 1 in here is 1. Plugging 1 in here is 1 cubed, but times a third is just a third. So I have 1 minus a third. 1 to the 5th is just 1 times the fraction 1/5 is just 1/5. The 7th power of 1 is just 1 times 1/7 is 1/7. And so this is what it looks like when you plug 1 into this polynomial and take an infinite number of terms, ... Okay, quickly, if I call this the 0th term, and this is the first term, the second term, third term, fourth term, and so forth, what's the formula for the nth term? Well, in absolute value anyway, you can convince yourself quickly that it's 1 over 2n plus 1. For example, right here, when n equals 4, 2 times. Oops, I forgot an n there. Try that again. 1 over 2n plus 1. 2 times 4, for example, is 8 plus 1 is 9. It's working there. It works here, and so forth. But I'm also interested in what does this term do as n goes to infinity. Clearly, it's 1 over infinity, and that's 0. That's good. One more thing to check. What about the n plus first term? What's its absolute value? The formula for that has to be 2 bigger than this, in the same way that 13 is 2 bigger than 11. That's 1 over 2n plus 3. Now, for anything you can plug into here for n, this term, which is just to the 1 to the right of this term, is smaller than that in absolute value. So that means this is closer to 0 than that. And finally, we have plus, we have minus, we have plus, we have minus. We have that strictly alternating sense. Okay, so this is a convergent alternating series by the alternating series test. So to what does it converge? Some number between 0 and 1. Well, what number is that? Okay, remember the tangent of pi over 4? That's the sine of pi over 4 divided by the cosine of pi over 4, which is root 2 over 2 divided by root 2 over... Okay, you know that tangent pi over 4 is 1. But now we're dealing with arctangent. And that means that tangent inverse of 1 is pi over 4. Well, this is what you get when you plug 1 into tangent inverse. So if you were patient and added up all these terms all the way to infinity, indeed you would get pi over 4. Does this calculate pi? No, it calculates pi over 4, which, by the way, is a number somewhere between 0 and 1. However, if you multiplied both sides of this equation by 4 here and 4 over here, and distributed the 4, you'd have pi on the right, and you'd have some expression on the left that looks exactly like this, except that there, instead of all these 1s, you'd have 4s. I'll show you what that looks like. It looks like this. And indeed, if you're patient with this, you can calculate pi. It's fun to try on a spreadsheet. It's also fun to see how many terms you have to add up to get anywhere close to pi. All right, it says use the tail of the 10th partial sum of s to put a bound on the error in approximating pi with S10. So here's s, and I want to take 10 terms of it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's S10. Here's the tail of S10, which itself complies with the 3 conditions of the alternating series test. So when we talk about error and trying to just calculate pi with only these 10 terms, we're saying that this can't equal pi because you didn't count all this stuff. And you can also know that this is smaller than pi for 2 reasons. The last thing we did is subtract. That pulls us down below the limit, and the limit is pi. And then over here, the first term of the tail is positive. And so the tail converges to a positive number somewhere between 0 and 4/21. So I'll write this up somewhat formally here. The error in using this to try to compute that has an absolute value of this. And that's equal to the tail in absolute value, which is positive, so you wouldn't even need it. But instead of saying it's equal to the tail, which we're not going to calculate, we're going to say the error is less than the first term of the tail, just because the tail is the error, and the tail adds up to a number somewhere between 0 and 4/21. Right? That's correct. Now, 4/21 is about 0.19. So it's actually a little bit bigger than 0.19. So anyway, that gives you a decimal feel for what our error is. Not what our error is. We know our error is smaller than this. And here's something to think about just before we conclude. It turns out our error is larger than the second partial sum of the tail. And you never see this when they discuss the alternating series test, but it's absolutely true. So if I go 4/21 minus 4/23, I get that. So your error is definitely smaller than that, and your error is definitely larger than that. And that's all I have to say today. Hope you learned something about alternating series, and hope you enjoyed this video. My name's Eric. Have a great day.